All right, so let's go ahead and get started. Homework 1 is due today, and that's due at 7 p.m., and it's due in that box that says EE245 in the courtyard. So you just need to turn it into that box in there. Do you know where that is? Not the courtyard, but the room where you hold your graduate student parties or on Wednesday or whatever those social hours, right? Homework number 2 is not online yet, but it'll be online very soon, actually. So next week, there's a couple things that are going to be going on. So one of them is the Berkeley Sensor and Actuator Center Industrial Advisory Board meeting. That's on Wednesday and Thursday of next week. And because of that, I'm not going to be able to be accessible those days. That means that on Wednesday next week, I will not be holding office hours. Okay, and it also means that on Thursday next week we will not have lecture during the regular time. I'm looking for a room time to do a makeup lecture. They haven't gotten back to me yet to tell me what room that is, but I'm shooting for Friday next week in the afternoon. So I asked for Friday 3 p.m. It'd be great if it could be this room, but I doubt it can because these rooms that can do webcasting are usually not available. And so what we will do is what I've done in the past, which is get whatever room is available. As long as it has a laptop projector, it's okay because I can actually use software on my computer to just record the lecture myself. So I don't even need the webcasting service to do it. I can do it using software on my computer. And so, you'll find out probably the next lecture where this is going to be. Okay, it doesn't end there though. The week after, I have to be gone again, which means that the week after we will have lecture on Tuesday, but there will be no lecture on Thursday again. And we'll try to do something similar, right? If I can find a room on Friday at 3 p.m., then likely that's going to be open the next Friday, 3 p.m. I think it's highly likely this room is going to be the Hogan room, which is just upstairs on 5th floor, which is what is the Hogan room? Is that 550 or 540 or 521 upstairs? Probably that's what it's going to be, unless we can get this room, in which case that's much better. Okay, but just a little bit of heads up that I'm going to be missing a couple Thursdays coming up, but we will do the lectures no matter what. Now, I'm not going to even ask you whether you can make the time that we choose, because again, it's going to be something that I'm going to record as I do the lecture on my computer, so you'll be able to go on the webcast site to watch that lecture if you yourself cannot be there in person. But I am setting it up such that whoever can make it can come if you want to. Okay? If you don't, then it's just going to be me in the room talking to myself. Usually in the past, people come, but not all of the class does, for undergrad classes that I've done this for. Okay, so those are my announcements. Any questions about anything before I start? Yes? 28th is a Wednesday. It is? Yeah. Okay, so it should be Thursday the 29th, which tells me that I asked for the wrong day for the room then. So I'll have to fix that. The 22nd is a Thursday, right? Yeah. All right, so it'll be probably Friday the 23rd and Friday the 30th will be those. Thanks a lot. So I got to remember to fix that in the email that I sent. All right, any other questions, comments? Helpful? Yes?
I don't know if there's anything to be done about this, but the webcast videos have
Really?
the most recent one.
That bad? Wow.
So it means when you're writing things out.
Yeah, I know what you...
See it.
Yeah, this has happened before, actually. And so they supposedly had upgraded all of their webcast services such that this doesn't happen anymore. But I guess that's not true. This is just the last lecture. Have you looked at any of the other lectures to see whether there are more... Anyone look at any of the other lectures to see if they're more synchronized with what's being written?
The first few lectures were okay.
Okay. Yeah, I don't know what to do about this because this is the webcasting service, and every once in a while this happens. I don't understand why that's the case, whether there's something different I can do on my computer. I will say that on the first day, where I remember my computer wasn't set up, so I had widescreen here, it wasn't widescreen there. I don't know if that's a difference there. But, you know, tell me if you see any of this happening on some of the other lectures. Okay, I will say that if I record the lectures myself, they turn out a lot better than the webcasting. Those who have been in my courses before are nodding their heads, saying, yes, that's definitely true. So why is it I just don't record it myself every time? Well, because it's not reliable. Right? What it's doing is it's using up a lot of CPU power on my machine, and it's possible that it can become corrupt, and then you don't get any web casting. Okay, so doing it is dangerous, but when it works very, very well. Right? Not only do you see everything much clearer, the sound is exactly synchronized, plus even this little thing, right? When I go to pen mode on this thing, I guess one complaint with what I do is that that little dot is too small to see. Even now it's small to see, and on the webcast you can't see it, right? But if I record myself, it creates a big dot there, and you can see exactly where I'm pointing at. So recording myself works very well, but it's not reliable, so I don't think you'll want me to keep doing that, because once it goes down, then we lose that lecture. Okay? The other thing is it creates a file that's gigantic, and so in order to get it to the webcast people, you can't just email it to them or upload it to some site. You have to give it to them. It has to be converted to another format that they have on the webcast site. That's a much smaller file. And so there's also logistical issues to doing that too. Yeah, but in terms of webcasts, I guess we get what we can. And they claim that they would be much better this year. They had a lot of upgrades, but apparently not good enough if there's a 20-second delay, at least on the last lecture. Okay. Any other comments, questions on these things? Okay, so today we're going to continue doing what we were doing last time, which was speeding through those process modules that I had up on the website. And so you have another module up on the website, which we're going to go through today, at least start into, that's going to be on lithography and etching. But right now we're still going through this first module that is on oxidation and film deposition. And last time we ended up about chemical vapor deposition. And again, you know, once we're finished with this, I'm just going to keep going into lithography, then etching. Okay? And so let me get out of this mode and get into the oxidation and film deposition here, where I've advanced too far. So let me. Okay, so where we ended up was talking about chemical vapor deposition and just looking at some chemistries that work for chemical vapor deposition. And the first one we looked at last time was polysilicon, and we went through this already, but I just want to repeat a couple things that I said. So last time, this is basically decomposition of silane, which is SiH4, under high temperature, 600 degrees C, into silicon, which deposits onto the substrate, and hydrogen, which of course can go away in the gas stream. So we talked about how that's one of the important things about these types of reactions. You need a reaction that creates the film you want, but at the same time, any byproduct from that reaction better be something easily removable, which means it ought to be a gas. Okay, and we talked about how 600 degrees C is a high enough temperature that the add atoms, remember how this works. You get an add atom that gets onto the substrate, it then migrates around, and it gets the energy from that for that migration through the temperature that's being put onto the wafer surface. And if the temperature is high enough, it can go long distances, okay, and then react with another portion that's seating in another area that happens to have a lower activation energy for reaction. And if you have a high enough temperature, then since the add atoms can move all around, you can get very conformal depositions. And what I mean by a conformal deposition, we talked about last time, that basically if you had even a MEM structure that looks like this, a conformal deposition would be one that can encase this MEM structure, not only covering the sidewalls where its thickness is the same everywhere, but even getting underneath structures like that and going into little crevices. Okay? If your temperature is high enough, you can do this because, again, an add atom that deposits here can move around and end up there and actually react. Okay? And polysilicon at 600 degrees C is one of these deposition processes where this happens. Okay? You can in situ dope polysilicon, so you could do that by adding phosphine or arsine gases upstairs, not upstairs anymore, in Satarja Dye Hall. The nano lab that we have can do this. Okay, so the polysilicon furnaces are all equipped with the ability to flow phosphine to get phosphorus in situ dope polysilicon. It greatly reduces the dep rate, like I talked about last time. A better process might be to add diborane, and so dope the materials p-type instead. That actually increases the dep rate. So your process for a given film thickness is much faster, but diborane is a very dangerous gas. All these gases are dangerous, but diborane is particularly toxic, and so they do not want to use it in a university fab, and thus we don't. All right, so this is where we left off last time. We were talking about silicon dioxide chemical vapor deposition. And so mostly I'm going to talk about LP-CVD processes here. And there's two cases that we generally need to be concerned with. One of them is deposition after metallization, where metals just simply cannot handle high temperatures. So for aluminum, if you have aluminum in contact with silicon, you expose that to a temperature greater than 577, you'll get a eutectic reaction. Right? A silicide could form at that point. You actually need lower than even that temperature, because even below that temperature, say around 500 degrees C, you can grow hillocks on your aluminum. So you basically, for aluminum, want to be below about 500 degrees C. Okay, for other metals like copper, even though copper has a higher melting temperature, you also need lower temperatures around copper, because in, say, CMOS type applications, circuit applications that use copper, they're usually surrounding these with very low K dielectrics. And it's the low K dielectric then that cannot take the high temperature. So, even though they've gone to copper for metallization now, the temperature ceilings on the latest CMOS and other transistor processes have gotten even lower because of these dielectrics that they're using around the metals. To reduce capacitance is what they've done. So you're looking for a low temperature reaction in this case, and to deposit oxide over a metal, and one such low temperature reaction is just silane combined with oxygen. You could do that from 300 to 500 degrees C. Lots of processes use 450, and that gives you silicon dioxide plus a volatile gas that can be swept out by the pump. If you want to dope this oxide, you can add phosphine to this, just like you do with the polysilicon reaction. This will dope the oxide with phosphorus. And so you might ask, why would you want to dope oxide with phosphorus? I mean, oxide is not a semiconductor. Phosphorus is not going to make it conductive. But what phosphorus will do is it will allow you to reflow the oxide. So what phosphorus does is it sort of lowers the melting temperature of the oxide to the point where you could take it up to a lower temperature than melting, and the oxide will actually reflow. So you're now talking about something where maybe you deposited the oxide over a structure like this. So that's your initial structure. And you deposited the oxide, so it's depositing at 400 degrees C or so, so that's not a conformal deposition. It may deposit like this over that structure. Okay, so it isn't conformal. And that, is some topography. We'll learn later on that we don't like topography, because topography is going to make it difficult for us to do lithography. It's going to make it difficult for us to do etching. So if we could avoid topography meaning large aspect ratios on this, if we can avoid that, we want to. Okay, so one way with phosphosilicate glass that you can do that is you can heat this thing up to 1050 or so. 1 hour at 1050 degrees C. And if you do that, then what happens is this phosphorus layer will smooth out. And it might smooth out into something now that looks like that above this. Okay, so it reflows almost like a liquid, so that it smooths out and gives you a surface with much less topography, where it's easier then to do lithography. Do you have a question?
Yeah, if you were going to reflow it at 1050 after deposition?
Yeah, that's a good question, I suppose. I guess the answer to that is, when I talk about metals and the problem with metals, in a lot of MEMS processes, you don't have metals around. Okay, so in a CMOS process, you wouldn't want to use 1050 to reflow the phosphorus. You could actually reflow it at lower temperatures too, right? It's just in our MEMS processes, we're usually using 1050 just to reflow as fast as we can. So it'll reflow at a much lower temperature as well. In fact, sometimes you want to dense, so there's a lot of different temperatures. 1050 if you want to reflow very fast. Also if you want to dope other things with the phosphorus, which is a process I'll talk about later on. 950 for 30 minutes actually densifies the oxide into a very strong oxide. So what happens is, once you deposit phosphosilicate glass, it's not a very good oxide. It's got a lot of gaps and pores and that sort of thing. So you can densify it by just taking it to 950 degrees C at 30 minutes. You can also even reflow at much lower temperatures as well. So what temperature you want to use, right, is up to you. It's just going to take longer if you do that. It's also dependent upon the doping, the percent phosphorus that you have in there. So phosphosilicon glass can be reflown, if you have 6 to 8 weight percent, you can reflow at 1,000 to 1,100 degrees C. If you dope it even higher, okay, you can actually reflow at even lower temperatures, but there's a problem with higher concentration of phosphorus, and that's that it starts corroding some of the metals around it. Okay, so it corrodes aluminum if moisture is present because it forms an acid. You get an acid around the aluminum that's like a phosphoric acid or so, and that starts corroding the aluminum there. Okay, so there's a lot of different processes here where you use phosphorus. In MEMS, we're usually doing 6 to 8 weight percent and doing this process to reflow it. Okay? I'll also say in MEMS, you can also use 5 to 15 weight percent phosphorus. You can go even higher because you might want to use it as a diffusion source to dope structures. And so one popular process in MEMS that I'll talk about later on is one where you actually have this kind of situation where you have a, well, I don't want to etch the device just yet. Hold on. Or maybe you have PSG here and PSG there, and this is polysilicon. And that polysilicon then will become your structural layer. In order to dope that polysilicon very uniformly, one thing you can do is just take this to a high temperature. Okay, and that temperature we usually take this to is 1050 degrees C. All right, and if you take it to that high temperature, then what happens is the phosphorus in the different films surrounding this film, right? You got a lot of phosphorus in all of this PSG around this. It will diffuse into the silicon, and it'll diffuse in a way that's very uniform, right, from the top and bottom. And so you get a very well-doped mechanical layer between the phosphorus if you take this up to high temperature. So that's what I mean by this right here, that this can be used as a diffusion source to dope silicon, and that's used quite often in MEMS technology. Okay, so before metallization, if you can use a higher temperature, you can get better uniformity and step coverage. And so there's such a thing called HTO, which is high temperature oxide. It's a slightly different process. You can take dichlorosilane mixed with nitrous oxide. It works best at 900 degrees C. And this gives you silicon dioxide, which is a nice conformally covering silicon dioxide that deposits at a good rate. Okay, so we have HTO at Berkeley, but we had been depositing it for the longest time, I think at a maximum of 835 degrees C or something like that. We just upgraded our tube to allow 900 degrees C deposition, which means you can get a much faster deposition of this HTO. And I'll say that in processes that my group does in research, we need this quite a bit, because we need to conformally cover the edges of structures with a high temperature oxide. Another way to put down a good conformal coverage of oxide is using a TEOS, so tetraethyl orthosilicate. This is basically, that's the formula for TEOS right there, and you're basically decomposing this at high temperature into silicon dioxide. Again, since this is a high temperature process, this also has excellent uniformity and conformal step coverage. So moving on from oxide to silicon nitride, this is another important layer to use for MEMS processes, I guess CMOS processes alike. I guess before talking about silicon nitride chemical vapor deposition, let me just first say that you can actually thermally grow silicon nitride too. So if you put silicon in an ambient of ammonia here and take that to high temperature, 1,000 to 1,100 degrees C, you will get silicon nitride. Very good stuff, but the growth rate is extremely slow. Okay, so that's the reason why people don't generally do this, where they will oxidize oxides. For silicon nitride, it's better, or faster at least, to use LPCVD reactions. And one of the reactions uses silane again, but this time combines it with ammonia. You could do this at atmospheric pressure from 700 to 900 degrees C. You'll get the silicon nitride plus a lot of hydrogens. There's also an LPCVD reaction which uses dichlorosilane. This is at low pressure now, LPCVD, and ammonia, 700 to 800 degrees C. Usually it's around the 800 degrees C that this is done, silicon nitride plus HCl plus some hydrogens. Now if you increase the temperature to 835 degrees C and you increase the flow ratios where the silicon is a little bit higher here, you'll get silicon-rich nitride. Okay, silicon-rich nitride is, people will argue, better than stoichiometric nitride, which is Si3N4, because it's lower in stress. Okay, and so that's not that important for a CMOS process, but for a MEMS process, that's everything. Okay? Now, the problem with silicon-rich nitride is it's not easy to run. It clobbers your pumps. And what does that mean by clobber your pumps? So in these reactions, right, you're flowing gases in, they're reacting. Then you get these byproducts that come out, and your pump has to remove those byproducts. Well, in silicon-rich nitride, the byproducts are nastier. So it's tougher for those pumps to remove them. They start clogging lots of things, and you're going to have to change your pumps. You're going to have to clean out the pipes that do this. And so there's a significant amount of maintenance required to run silicon-rich nitride, low-stress nitride. And so as a consequence, there are really only two places that run this right now as universities. You're at one of them, so you're lucky. Right? You have silicon-rich nitride. If you're a MEMS person, you have it here. I think Cornell also runs silicon-rich nitride. But those are, I think, the only two that are doing it right now. Other universities could do it. Michigan used to do it, but they gave up after a while because they didn't want to keep cleaning clobbered pumps and that sort of thing. Okay, but we're willing to do it because it is an important step in some processes out here. Just some comments on LPCVD nitride films. They do end up being hydrogen rich, right? If you look at these reactions, a lot of hydrogen involved. So you get some of that hydrogen in the film. If you're depositing stoichiometric nitride, the Si3N4, these have high internal stress. Okay, so that's what you're trying to avoid with silicon-rich stuff. So if you don't deposit silicon-rich, you end up having cracks in your films, and they start peeling from your wafer surface when they're greater than, I'm saying greater than 100 nanometers. You can really get to about 300 nanometers, and at 300 nanometers, that's pretty much it. Things are going to peel off of that wafer just because of a high stress. And so why do things peel off of wafers because of a high stress? Well, we'll go through that later on in the course in much more detail. With silicon-rich nitride, though, you can get 2-micron thick films without big problems. Okay, it could be very low stress material. You can make structures that are suspended that, if designed correctly, do not buckle and are not bending in and out of the plane of the wafer. LPCVD gives you good stuff. So it gives you very high resistivity films with good dielectric strength. There's another way to deposit this nitride, and that's PECVD. And so here are some of the reactions here, right, in a nitrogen discharge or an argon plasma here. The PECVD, remember, PECVD is where you're doing it at lower temperature, but you are supplying energy for the reaction to occur and to get a conformal deposition, if possible, using plasma. Okay, so that energy is coming from the plasma. This is even higher in hydrogen content. People will say that you can control stress in this by changing the recipe. So in this, you can control how you deposit, right? You can deposit a little bit of the film at one recipe, change the recipe, deposit another film. So if you know the first recipe is tensile, you put a compressive, tensile, and you balance out the stress out of this whole thing. You can do that in PECVD, but it's hard to control, especially at a university. So if you were designing a process that required a mechanical structure in a PECVD film and you wanted to play this trick to get that structure to be nice and straight, be prepared to spend a lot of time characterizing that process. And then once you've characterized it, if you leave it for a month and then come back, be prepared to characterize it again. Okay, because PECVD, unless it's used again and again, and this goes for all semiconductor equipment, unless it's used for one purpose over and over and over again, it's not going to be repeatable. Right? The way that foundries are able to get repeatable silicon and even repeatable MEMS now is they dedicate a tool to doing one and only one thing. So it's always dialed in. At this university and at pretty much all universities across the nation and the world, no tool is dedicated to one purpose because we simply don't have the space and the money to do that sort of thing, right? So some of the etchers upstairs, some of the PECVD systems, they're depositing lots of things over lots of different substrates. And tiny changes in contamination or conditions, that can cause drastic changes in how those tools perform. Okay, so as you're doing research here, just keep in mind that this is not an industry foundry. You cannot plug your wafer into a certain tool and expect it to do what it says it'll do. Right? You better test it first to make sure, because you don't know what the person before you was doing in that tool. Right? And even the person before you with maybe a little bit of metal on their wafer or so before you came in, that could change everything for you. Right? I guess that's part of the reason why my guys in the lab, MEMS guys, have a big target on their backs, because the device guys don't like to see them in certain places. Because CMOS is especially sensitive to contamination, right? So I understand that completely because I ran CMOS when I was a student here, right? I didn't want to see any MEMS guys, even though I was a MEMS guy, around my process. So I understand the device guys here, but now my students are the MEMS guys, so I got to defend them a little bit. But these are things to be careful about in the lab. That's why when there's a rule about cleanliness, you follow it, okay, whether you're a MEMS person or not. And lab etiquette's very important, right? If someone's not following the etiquette, you should report the person, right? Yeah, they'll get yelled at and that sort of thing, but you got to keep the lab clean. Otherwise, it hurts everyone in research. Okay, CVD for metal. So we talked about putting down metals using sputtering and using evaporation. Those are still very popular ways to put down metal. But you can also put down metal using CVD processes. And these become a lot more interesting if you're a MEMS designer or doing MEMS research, because sputtered metals and evaporated metals, they're just not all that good. CVD metals can be even better in terms of material properties. And so one recipe you can use, for example, for tungsten is take tungsten fluoride here and decompose that there, or a reaction with hydrogen to decompose that is possible. We don't have this in our lab, but Stanford used to have it. I don't know if they still have it or so, but it's very possible to do. You could do it with other metals too, where this is a generic formula where M is whatever that metal is. Could be molybdenum, tantalum, titanium. Even aluminum can be CVD'd. But for aluminum, other methods so far, I mean, for at least ICs, other methods are better. But actually, for MEMS, CVD would probably be better. Copper is normally electroplated. A lot of these metals can be electroplated as well. What is electroplating? I'll talk about that later on. Okay, so now epitaxy. This is a way to put down, yes?
All right, a quick question about CVD. I know you can CVD.
Yeah, oh yeah, my group is, actually we did a lot of the early work in that, of actually putting CVD diamond and using it to make mechanical resonators. The reason why it makes sense for resonators is it has a very high acoustic velocity, so it's much easier to get these things to vibrate in the gigahertz frequencies. Yeah, but we're doing that. We actually bought a new CVD diamond reactor tool that's going in our lab. I think it's going to be installed sometime mid this month or something like that. Yeah, so everyone will have. Our lab means the nano lab, right? Not my lab or so, right? If I buy anything, I put it in the nano lab. Okay, if you have advisors that do the same, you need to encourage them to do the same thing. I guess I'll put that message out there, right? Because we can all share this equipment in the common nano lab. But yeah, diamond is good stuff, actually. And I think in my group, diamond will replace polysilicon completely if we can, yeah, for the types of devices we're doing.
Can you use it as effective heat sinks as well?
Yeah. Oh yeah, diamond. It's got all these nice properties, right? It's thermal properties, it's quality. It doesn't contaminate as easily as polysilicon. It's more resistant to contamination. There's all sorts of nice things about it, actually. All right, so now epitaxy, going back to silicon, I suppose. This is what you can use to deposit on a silicon wafer. If you start with a single crystal silicon surface, you can continue to deposit single crystal silicon over that single crystal silicon surface using a deposition, a CVD process basically, called epitaxy. The difference here is there's different temperatures, there's different purities required to do this, but not that different from CVD. So I'm really not going to talk about this. I'm just going to, you have slides here, you can read through this. You can also read through your book on epitaxy. But I'm just going to skip all this stuff here and let you read this by yourself, because it's the same stuff as CVD. Okay, it's really the same thing. It's just now growing single crystal silicon over single crystal silicon. And in some MEMS processes, that can be important. For a lot of IC processes, it's very important, because that's how they make the starting wafer in ICs, both bipolar and MOS. Okay, but I want to move on to talk about another deposition technique, and that's atomic layer deposition. This is the newest type of deposition that people have come up with, and admittedly, it's the chemists that really came up with this and did a fantastic job with this. So if you look at today's CMOS transistors, so it used to be that CMOS was possible, whereas other types of semiconductors like gallium arsenide, indium phosphide were not as easy to do as CMOS. And the reason for this is because CMOS in silicon had a great oxide. Okay, you could grow an excellent silicon dioxide over silicon. Okay, well, it turns out that you no longer need to grow that excellent silicon dioxide, that no one is using, well, okay, that the most advanced CMOS processes are no longer using silicon dioxide as their dielectrics, but they're using other dielectrics that have higher permittivity, so what's called high K dielectrics. Things like hafnium dioxide, even titanium dioxide or so. These are things that have permittivities on the order from 20 to 80, whereas silicon dioxide, of course, is on the order of about 4, right, 3.9. So that much larger dielectric constant makes it easier to make transistors because you don't have to make the gate as thin as before. Okay, and that does a lot towards making the transistors more reliable, etc. Okay, and you can scale them much better. Now, the key technology that has enabled all of this is atomic layer deposition. All right, and so what is atomic layer deposition? This is it's mainly a chemical reaction, but it's interesting because it's a self-limiting reaction. Okay, so the way that it works is sort of pictured here. You take a substrate that has nothing on it. You feed in what I'll call precursor A. Okay, precursor A will react with the substrate surface, and it will form a half layer, I suppose I'll call it. That's part of the layer that you want to build up. But the nice thing about this is it'll coat this substrate, but as more A comes in, it's not going to react because it's coated that substrate with itself, and it doesn't react with itself. Usually that's the case. Okay, so once you have the substrate completely coated with a single layer of these atoms, okay, you then flush the system of all the atoms, and then you let in precursor B, which is really the reactant with A. Precursor B comes in, it reacts with A, and it creates a layer that B no longer reacts with. Okay, and so again, this is something where a second monolayer, or a single monolayer of the molecule that you wanted to form is now on the surface of your wafer, and no more reaction can occur if it's surrounded by B. But if you then push A back in, it's going to react again. And so you can see how this works. You just let in one precursor at a time. Okay, and every time you let in a precursor, you're building this film, a monolayer of molecules at a time. Okay, and so that tells you a lot, right? You could be very accurate about exactly how thick that's going to be, because the thickness is going to be entirely dependent on how many times you've done this reaction, how many times you fed A and B in, right? How many cycles of this. It could be very conformal, because it's a gaseous reaction, right? You get a monolayer, can go underneath things, it can go into very deep ditches and stuff, as I'll show you very soon. Very interesting reaction, and you can get films with very good quality here. You can get bad quality ones too, but if you do it right, you can get very good quality. And so this I sort of said already. These are just those remarks that I was saying in the last slide, but just written down here, right? Complete self-limiting half reactions. You basically control the thickness in a digital manner by just counting the number of cycles. I guess I'll add that the reactions between A and B, they don't have to be chemical. They're often chemical, but they can also represent physical processes. Okay? Yes?
Is from before epitaxy, I think, referred to, is that
You can do epitaxy of different things too, but usually silicon is the one. So if you have a crystalline structure, you want to grow more of that crystalline structure, it's the same kind of thing. You're putting the gases in, you're taking it to a high temperature. No, you're actually growing. You're growing. In epitaxy, you are growing. Just like you're growing in a CVD process. It's a chemical reaction that's occurring, right? But, you know, it's not like this, where this is growing a monolayer at a time. This is very well controlled. Oh, okay. Yeah. But epitaxy, yeah, it's no different than LPCVD, than CVD, I suppose, except different temperatures. There's a little more to it, too. So in the epitaxy reactions they use for silicon, you can get both deposition and etching. Okay, but again, those things I'll just let you read about, and then you can ask me about those in office hours or so. It's not as important for MEMS. That's sort of why I'm skipping over it right now. Okay, so more advantages of ALD. I think I just talked about it, right? Surface limited reaction, excellent step coverage and refilling. All these things I sort of talked about. The other advantage here is that it's not that sensitive to flow rate and temperature. It is sensitive to that. So there's a process window where you get good ALD. Okay, so you want to stay within that window, but that window is quite wide. All right, if your temperature is not exactly, at 400 degrees C, it's still going to work, right? In an LPCVD furnace, you have to pay attention to what that temperature is, right? Because that temperature decides how fast that layer grows. In this case, it's not really the temperature that decides how fast the layer grows. It's how many times you cycle the two reactants. Okay, so it's less dependent on temperature, and that's why you have better control when you're depositing an ALD film. So a typical ALD reactor is pretty simple to build, right? It may look something like this. You have two baths that control your precursors, and then you have some high-speed valves. And the better tools are the ones that have the faster valves, right? And can flush out the reactants faster, because that means they can deposit faster. Okay, and so what you'll do is open this valve, let that in, let it react, shut it. Open this one, let that in, let it react, shut it. Pump out the stuff through each of these cycles. They're a very simple tool. And actually, Ali Javi, when he first came here, just built his own ALD tool. Right? I think he spent $20,000 to build that ALD tool. And we tried using that. And that kind of tells you, he built that for $20,000, and then we bought one. I bought one for $300,000. That's in the lab right now, the PicoSun that's in the lab. The difference is night and day. The PicoSun is pretty darn good, at least for our process, right? So you can make one for cheap, but you have to keep it dialed in is what it means. Right? If it's not dialed in very carefully, then it may not perform as well as the big ones that you buy. So you do get what you pay for in ALD. Okay, so here's an example of the ALD reaction here. And so this is just at the molecular level. So usually what happens is you start out with your substrate. Maybe that's just bare silicon. For most of these reactions, you want to hydroxylate the surface. And that way you just put water vapor in there. Just water vapor from the air gets on the surface of your structure. And usually what you end up seeing is bonds, OH bonds just sticking out from the surface. And then you've got a monolayer of these things covering the whole surface. And so usually in ALD, you're looking for a first precursor that will come in and react with these OHs that are sticking up. And it turns out that trimethyl aluminum, which is aluminum with 3 methyl groups here, can do that. This comes in, it reacts, it releases methane as it does this. Okay, that methane can be flushed out, and that methane doesn't continue to react with this. And so you end up with this layer here. Methane doesn't react with this. More TMA comes in and doesn't react with this. Okay, so that ends the reaction right now. Once you have this monolayer, that's it. No more reaction. Okay, you can flush out this gas and then start introducing the next precursor, which in this case is going to be water. Okay, so water vapor comes in. It reacts, right, to release more of these methane groups here. And it continues to react with all of these until it creates another monolayer here, where you have your alumina here. You can see the alumina start to form, the Al2O3 on this. And you can see what you end up with is a situation where you have hydroxyl groups, again, sticking up. So this is now fresh and ready for introduction of the TMA again. And then you grow each of these one at a time. This one, this one, this one. Every cycle, you're going to get another of these. If you know how big this molecule is, then you can calculate how many cycles is required to get a very exact thickness of film here. Yes?
Is this single crystal when you grow it like this?
Is this single crystal when you grow it like this?
Or do you get single crystal aluminum oxide when you grow it?
I guess I don't want to answer that complete. I mean, it looks like it's single crystal at this point here, but it really is an oxide that's growing up. I don't think it's that perfect in the end, because I know that you can get variances between different ALDs. Alumina is pretty good. So with alumina, I'm kind of hesitant to answer that, to say that it's not really single crystal, because it actually is pretty good. But definitely with other ones like titanium dioxide, hafnium dioxide, at least when we've tried it, we don't get a consistency that tells us it's single crystal. Okay, so you can still, I guess in our assumptions, we usually just still assume that it's more of a glassy type thing. But it is a very good film, right? The alumina comes out to be extremely good, yes.
What happens to the OH groups that are at the topmost?
They just sit there. You mean after you're done with ALD?
You're done.
Yeah, they just sit there. So, I mean, everything has an OH group on it, usually, right? So water gets on everything, and it just sticks up on that. And so I guess if you introduce more TMA, you can grow another layer, monolayer above that. But at each step in this, right, you essentially end up.
With the topmost layer.
Yeah.
So if you wanted to deposit something else on top of this, would you?
No, if you were going to do ALD again, you'd want those OH groups there.
Right, but if you're done with ALD and you're depositing another layer of something else.
Yeah, so usually if you deposit another layer, if you go into an LPCVD furnace, you're going to be at very high temperature. So you're going to get rid of those OH groups anyway. Okay, and deposit your film over that. Okay, so this is what you could do with ALD here. And I guess at this point I can also show you the little video, which I guess is advertisement for a company that does ALD, but it's a nice video. So this is their reward for making such a nice video. This is a Cambridge Nanotech's video on ALD, and so this is just going to animate for you. Did this start? Okay, so this is going to animate for you, the tool that they have. So there it is, put the wafer in. Pretty simple tool. This is an old version of their tool, actually. And let in first precursor, flush it out. Let in the second precursor, flush it out. And it can happen this fast here, even faster than this, actually. And then looking at the details, suppose you're trying to deposit a coating over these very deep trenches here, like for a trench capacitor or something like this. And so what's really happening on this, so there's your hydroxyl terminated surface. There comes the TMA that reacts. And, a single reaction shown. I guess it's going to fill up the whole thing there. And as soon as you create the monolayer of this, these come in and they don't react anymore. You flush those away, then you let the water come in. These start reacting, and you put in more water there until you create a surface here, and now water doesn't want to react with this surface, and you continue doing this until you get all of the different layers that you want. And the coverage is very conformal. It's a gas that gets into all these little crevices here. And so not only is it a great way to create dielectrics for MOS devices, but it's a great way to create very deep trench capacitors with very high capacitor densities. Okay, so a little animation of how that works. And let me go back to this module here. Okay, this is just, an actual SEM of a deep trench that has been coated with a very thin layer, 18 nanometers of alumina here, using the exact process that you just saw. Yes?
What's the surface preparation before doing
Well, usually we're not doing a lot of surface preparation, at least for silicon, because silicon will grow these hydroxyl groups there. I guess for other films, so for alumina, there is some dependence on how well those hydroxyl groups grow. So alumina, when it deposits, it doesn't require that uniform a forest of these hydroxyl groups. But titanium dioxide, for example, does. So if you try to do titanium dioxide directly over silicon, without any surface preparation, you'll get a titanium dioxide film that's not very good. What you have to do for a lot of those types of films, you have to put a very thin film of alumina first. Maybe put 3 nanometers of the stuff. And then on the alumina, you'll get a very dense forest of the hydroxyl groups. Then the titanium dioxide can come in and form very well over that alumina. So there's some art in ALD. You know, there's some ordering of layers that you want to put down to ensure the best films. Okay. All right, so just a chart that says a few things about ALD versus CVD. In ALD, you have very reactive precursors. Okay, in CVD, they're less reactive, so they require a higher temperature to actually react. In ALD, the precursors react separately on the structure. In CVD, they can react at the same time on the substrate, so they come down and react and deposit the material on the substrate. In ALD, the precursors must not decompose at the process temperature. In CVD, a lot of times they're designed to decompose at the process temperature. In ALD, uniformity is ensured by the saturation mechanism. In CVD, uniformity requires uniform flux of reactant and uniform temperature. That's difficult to do. Thickness control in ALD just counts cycles. Thickness controlled in CVD, very precise temperature, very precise everything. So difficult to do. ALD, you can have a surplus of the precursor doping. You don't even care what the concentration is because the reaction stops itself. CVD, you better pay attention to those flow rates and exactly what that concentration is around the stuff that you're depositing on. Okay, so lots of advantages with ALD. It's a lot easier to put together and actually operate. This is just a big chart that compares different methods for depositing materials. I won't go through that, but I'll let you stare at that later on if you want. But I'll move on to yet another method for depositing films, this time metal films, in MEMS processes, and that is electroplating. Okay, so what is electroplating? That's the same experiment you ran when you were in high school or junior high school or something, where you had those big beakers and you made a battery out of that, right? This is just really a battery, except the goal of this battery is to deposit a film on something. Your high school experiment probably deposited things on a spoon or something like that. Okay, so this is a process where you're actually using electrical current to take ions out of solution and actually from an anode and coat a cathode with that material. And so the way that this would work, this is useful when you want very thick films. Okay, so we can already put metals down, right, using sputtering, CVD. I even talked about LPCVD to put metals down. When do you want to use electroplating? That's when your thicknesses are very thick. Okay, so if your thicknesses are greater than 1 micron, which is often the case in MEMS, you probably want to do some electroplating. Okay, so how do you do this? So you create this setup. This is a beaker containing copper sulfate. I think that's sulfate. It could be sulfamate. It contains this solution here with a copper anode and just a cathode here, just any piece of metal, I suppose, a spoon in this case. And so the way this works is you put a battery between these two, and the battery will suck away electrons from the copper. If you have this copper sulfate solution here, copper ions will go into solution, and they'll go, right, because of the electric field across these two, they will travel from the anode to the cathode here. And once they get to the cathode, they'll recombine with the electron, which means they deposit onto that spoon. Okay, so it seems like a very, very simple process, but it actually is. It is very simple in your high school lab class, right? Because you'll grow a film over that spoon. But do you remember what kind of film you grew? It was more like fur, right? It wasn't a very nice uniform film. It was like fur growing on that spoon, right? And so that's where you have to. It takes a lot to control this process. And if you want to use this process to create a very smooth film, it's not as simple as this. You have to be very careful about current densities. You have to be careful about the solution. You have to be careful about how much current is being used to actually do this electroplating. You also have to change the way that you do all of this. So if you're trying to electroplate over a wafer, then usually what you have is a special holder for the wafer. And not only that, you have to put a seed layer on the wafer first. So you have to make the wafer conductive, okay, so it can serve as your cathode in this case. And the way that you do this is you start with a silicon substrate. You may put down a dielectric layer, a couple dielectric layers, maybe put down through sputtering some kind of interconnect layer that you pattern. Then you can you can sputter some aluminum on top of this too, or electroplate that aluminum. Cut into that aluminum using an etch that we'll talk about shortly, and then do this electroplating here. But you'll notice that as you do this electroplating, the whole wafer is covered with a metal. Okay, that allows the current, which is necessary for electroplating to occur, to get to these portions here where electroplating occurs. Okay, you also see that you can't necessarily electroplate over every metal. There are different metals that you can electroplate another metal over. Right? In this case, if I have aluminum here and I have Ti gold right here, then the nickel doesn't really plate above the aluminum. Okay, but it does plate over the Ti gold. And so you could actually use the aluminum in this case as a mask for electroplating the nickel. Okay, there are some cases where nickel will electroplate over aluminum. Okay, it depends on your solution. It depends on a lot of things. Okay, so it's very chemistry dependent on this. But in this, then you put a seed layer down, this time of all nickel here. Maybe put a photoresist around this to mold the electroplating. And then when you've molded this, you get electroplating only between those molds. That creates the structure. You can then remove that photoresist mold. And then at this point, you have to dip the whole thing in an etchant that attacks nickel. That's going to attack some of the structure too. But if the structure is much thicker than this seed layer, you'll just get rid of that seed layer. Okay, then you attack the aluminum and aluminum only. Do I? No, I don't. Okay, so the aluminum ensures the electrical content. The final step of this, which I don't show, is removing that aluminum. Okay, I showed that in a previous version of this process, though, in a previous slide. And so this is what people use to do this, right? Same thing. You got a solution, in this case nickel sulfamate, and you put it at the right temperature, you give it the right current levels, and you will electroplate different types of films with different types of current levels. So films with different types of granularity, some smoother than the other. You pretty much have to figure out the right recipe to put down good films for MEMS purposes. You have a holder here that ensures that you can get electrical currents around all edges of the wafer, so it's in contact along all edges there. That gives you very uniform current distribution around this wafer, which gives you very uniform electroplating here. And the rest of this, right, is just like the high school experiment. Right? It is the high school experiment, except you're being more careful about the solutions you use, the concentrations, the currents that you're driving with. Okay? Okay, and that's it for film deposition and oxidation. Okay, and so as promised, I'm just going to keep going here and go to our next topic, which is lithography and etching. Okay, so let's start with lithography here. And these are the topics that this module goes through. So this module is online or will soon be online. It just has to be posted. But you'll have all these slides too. We'll go through lithography, what it is, how it works. Then we'll talk about etching, wet etching, dry etching. I guess these two are very important for MEMS processes. Deposition is definitely important too. These also extremely important. And then we'll go through semiconductor doping in this module, which I'll go through fairly quickly because that's important for MEMS, but not nearly as important as it is for things like transistors. Okay, and transistors usually want doping levels at a very certain concentration. In MEMS, you don't care. You just want to dope the heck out of it to make it conductive. Lots of times you want to do that. All right, so lithography. What is lithography? This is a method for patterning massive numbers of features on a wafer. So you can pattern billions of devices, more, today in just a few steps. Okay, this is the beauty of the whole silicon IC process. Wafer-level fabrication is all based on lithography here. And so what does it consist of? It consists of a radiation source. Okay, so this is a source of some kind of light. And it's not just optical light, right? It could also be, even anything with a wave nature, right? So E-beam can be used. Different types of beams are usable. We'll talk about those in a second. But this radiation source then has to move through some kind of mask here. Okay, and this mask could be made of glass or quartz, and it's going to be different depending on how much you want to pay, what kind of resolution you need, and what kind of light source you have. It passes through this mask, which has patterns on it that sort of define the types of structures or CMOS gates or anything, whatever that layer is. This pattern defines that. And this pattern is basically something you drew in computer. Okay, so if you're a circuit designer and you actually end up doing circuit design, a lot of what you'll be doing is doing layout. Okay, especially if you have a master's degree or something, right? These days, they don't even let a bachelor's degree person do layout. They'll ask the master's degree people to do that, and then the PhDs do the designs, I suppose, and a lot of these companies that are doing silicon transistor type stuff. The reason for that is it's so competitive right now that you got to get your transistors to work on the first pass. Right? You can't afford to have them fabbed, test something that's failed, and then have to redesign that, because if you have to do that, your competitors already beat you. Right? So it's a very cutthroat sort of thing now, so you have to be really good to do this stuff. But this mask is really drawing. If you're an analog designer, it's really coding a computer program that automatically draws it for you if you're a digital designer. Okay, so that's what it comes down to. This is very much automated. Okay, so and that's how we can do circuits with billions of transistors, right? Human being doesn't want to sit down and lay out billions of transistors, right? You better have some computer program that helps you do that. In addition to this in this process, the other important thing is some kind of photoresist. Okay, so this is some kind of resist material that's sensitive to light that can be patterned by that light. And then what you can do is etch whatever features you pattern in your photoresist into the layer underneath it. Okay, that's what we're trying to do. We're just trying to pattern a photoresist so it creates the pattern we want. And we really want that pattern in the film under the photoresist. And so we'll etch that film. The photoresist hopefully will protect that film from the etch. Any exposed places will be etched. Okay, and finally there's an exposure system in this, which is a system that sort of, it's step and repeat. It contacts the mask to the wafer if applicable. We'll talk about all these in detail now. So let's start first with the basic process here. Okay, so we have light coming in through a mask. So this is the mask here. These are the opaque layers on the mask that define the pattern. And this blue is the light that's getting through this mask to the photoresist atop the film on the silicon substrate. Okay, so you can see this photoresist is being exposed in these areas where the light is hitting that. Okay, if it is a positive resist, then, and there's such thing as a positive and negative resist, but if it's a positive resist, then when the light hits the photoresist, that's an area that can be removed. Okay, so that photoresist is weakened, I suppose, such that it can be removed later on, so that you're left now with photoresist patterns here that mimic the patterns that were on the mask. Okay, you then can go on with an etchant that then etches the film underneath that, so that now the film mimics the pattern of the photoresist, which essentially mimics the pattern on the mask. Okay? And you can make these patterns very small. Right? This is how we get our tiny resolutions. What is it? 24 nanometers now is what people are doing with light using in semiconductor processes. So you can get these very tiny. You can also expose billions of transistors, billions of features at the same time, all at once, in a flash, just a few seconds, done. Okay? So lithography is very important, right? It's sort of the backbone of a lot of these processes, whether they're integrated circuits or whether they're MEMS. A lot of times you will judge how expensive a process is by the number of masks that it uses. Okay, so this is sort of showing by time. In the beginning, NMOS, right? No one does NMOS anymore. People do CMOS, where you have both NMOS transistors and PMOS transistors on the same chip. But in the beginning with NMOS, that was 4 to 6 masks. Bipolar then became the rage for a while because it was faster than NMOS or CMOS at the time. That was more complicated. That's 8 to 15 masks. Bi-CMOS came around. That's about 20 masks. And now everything is CMOS, mainly because of power consumption and complexity. But everything is now CMOS. I'm saying 8 to 28 masks. This is actually an older slide. It's actually on the order of 40 masks now. for the number of steps that you need to do some of the more advanced CMOS processes that include all sorts of things now, not only getting small features and using ALD gates, but also introducing stresses into the structures to get higher mobility and that sort of thing. There's a lot of technology going into CMOS here, and they are very complicated processes. And so now let's contrast that with MEMS. MEMS, comb drive resonator that we'll talk about, 3 masks. Okay, these gigahertz disks that we talked about, 4 masks. Okay, so MEMS compared to CMOS, extremely easy from a mask count standpoint. Not easy from a stress standpoint. Okay, but once you get that stress down and you want to make a MEMS product, the MEMS product is going to be very cheap. Okay, depending on what kind of product it is. So I could say that for my company, for example, we make oscillators, right? It's actually the transistors that cost more than the MEMS. Right? The MEMS are almost 0 cents versus the transistors. Right? So that's where we are with these MEMS processes. And that makes sense, right? Because there's so few masks going into making the MEMS process. The yield of the MEMS is so high that it's almost a no-brainer now. And it's just the transistor and the system that causes yield losses that cause cost increases. Okay? So let's take a closer look at the whole lithography component here. First, the radiation source. Okay, so there's several types of radiation sources. I mentioned optical. Okay, so this means visible light, UV light, deep UV light. But there are other types of sources. E-beam, X-ray, ion beam type lithography. I'm sure you've all heard about these things. And they all differ basically in the wavelength of light that you're using. Right? The shorter that wavelength, or the wavelength of the phenomenon you're using, I won't call them all light, right? The shorter that wavelength, the better the resolution you'll be able to get. Okay? And today's prime choice, even though these have shorter wavelengths and so therefore should be better, today's prime choice is still optical. Okay? And it's optical because of many reasons. Optical is a very high throughput. Right? So cost is the biggest thing. Okay, and you know, CMOS is a very interesting field because it's one of those fields where you don't listen to the experts again. Or maybe you listen to the experts, but only those experts that are doing stupid things like creating roadmaps. Right? When you create a roadmap for something, you're not really thinking too much about how you're going to do it, right? Because so if you look at the roadmaps for ICs, right, how do they come up with these roadmaps? You know Moore's law, right? Is there any theory and science behind Moore's law? No, right? There's just a line. There's a line, right? That's all Moore's law is. It's a line. And so all these roadmaps, they're all just plotting lines, right? And saying, okay, at this day we're going to be here. At this day we're going to be here. Right? So what happens, right? And this happens at IEDM, right? This was back in 1985 or something, right? There were some people getting up saying, that's it for CMOS. No more silicon. It's all going to be gallium arsenide. From this point on, 1989 on, that's it, gallium arsenide, no more CMOS. Okay, what happens? Right. You don't see gallium arsenide anywhere, except in LNAs and that sort of thing. It's still CMOS in everything, right? And how did that happen? That happened because people were geniuses right along the way. They had this roadmap, and if you put enough effort into it, you could probably achieve what you have on that roadmap. So just a little more for you in your research, right? If you're doing a research problem that you know can be done, you're going to get bored fast, right? So if you're choosing research to get a PhD here, don't choose something that you know is going to work, right? Choose something that you think a lot of people think are not going to work, right? That's a lot more fun because you're probably going to get that to work. Or you're going to discover something that's a much more interesting research project and head in that direction, right? It always works out. But don't be risk averse when you're choosing a PhD project. Choose something that is very high risk because the returns on that are extremely good, right? You'll be much happier with the high risk thing. I've had many students, right? Types that choose very conservative projects, types that choose very aggressive projects. They all end up graduating about the same time, but the ones who chose the aggressive projects made the much bigger footprint, the much bigger impact on the field. All right, so just keep that in mind, right? I mean, you could see that in CMOS, right? People look at the CMOS roadmap and say, ITRS, that's impossible. That's just stupid, right? You see people now saying, okay, we've got to change the roadmap now. Maybe the line can't be like that. Maybe we've got to move the curve like this. And people are doing this now. And what's happening is, you know, after they change the curve to change the slope, the point comes up here where they should have stayed on the original slope. Okay, so that's what's happening with this, and that's lithography has been the most interesting thing on this, right? Because when you look at the wavelengths that you can use with optical, right? Yes, we are going to better wavelengths. We're now at deep UV, and so this shows optical source. If you have a mercury arc lamp here, you can get different types of lines. So there's I line, there's G line. We have both of these in our lab. You can see the wavelengths they're associated with, and yes, I line can get better resolution than G line. Okay, our lab actually also has deep UV here, which is even smaller wavelength than that, but it requires an excimer laser to actually create that light. And an excimer laser is very expensive. Okay, so that's why our ASML stepper in the lab is a very expensive lithography tool. And you know, that's not even state-of-the-art anymore, right? There's much better stuff out there that Intel and the rest are using. Okay, but there is a limit to wavelength, right? I mean, there's a theory behind this, and so how could people beat the theory? Well, there's different tricks that people have been playing, right? That some of it's in the mask, right? They're now using masks that are phase-shifting masks. And actually, phase-shifting masks can actually improve the resolution versus what you thought you had before, but it takes a little more energy, work to create that mask now. So the mask cost starts rising as we get to these finer and finer feature sizes. I guess I could tell one story, the excimer laser person. So I knew the guy who actually started excimer lasers, actually. This was a guy who eventually went to DARPA. His name was Joe Mangano. And he started a company on these excimer lasers, and there was a time when his company was selling all the excimer lasers for the photolithography tools out there, right? And so you'd think that he made a lot of money, but actually no, he didn't make all his money off of that company. He took the money he made, invested in real estate in Boston, and that's what made him all his money. Okay? So he's a very rich man right now, and I will warn you, don't get rich, okay? Whatever you want, don't get rich. Okay, and the reason for this is because once you get rich, okay, I'm being recorded, so this has nothing to do with him. This has nothing to do with him. I know a lot of rich guys out there, right? But once you get rich, right, you start getting, you know, you lose your drive, right? So you don't want to do things anymore, right? Because you made it already, right? So maybe you like that, right? But you'll see, right? All these guys that I know have hit it real big, right? That's enjoyable for 6 months, but it gets real boring. Right? You go off to a nice island for a while. You can only stay there for 6 months. And you will get bored if you're this type of personality. If you're here, and you're sort of a type A personality, right? You want to do something. And you'll find that once you've made it, right, it's tough to do something. Because, right, when it hits the midnight hour, and you got to burn the midnight oil to get something done, right? If you need it, you'll do it. If you don't, let's just go to sleep. Anyway, something to think about. Also, once you get rich, all you do is you worry about your money. That's it, right? That you have lots of money, you just worry about it all the time. Why am I telling you this when we have to move through this very quickly? I don't know. I just have to for some reason. Okay, so let's go to the mask now. So the mask today has become one of the biggest bottlenecks to processing. Okay, so it's actually the thing that constrains a lot of things here. So what is the mask? The mask is the most convenient thing in the world, right? You take your device design, transistor, MEMS device or so, you lay it out, which means you draw it, or you let some program draw it for you on computer, right? This is just like using your drawing programs to create a drawing, except this drawing is just full of boxes and circles and different things on top of each other. And then you take that file and you generate a mask from that file. And usually that mask is generated on fused silica glass or quartz, where quartz is more expensive, but quartz has a smaller thermal expansion coefficient, so is better when you're going to smaller feature sizes. And so I guess I'll talk about why is it that this thermal expansion coefficient is so important. So I can draw some pictures here. So say this is your wafer. And this wafer, usually what you're trying to do is align a new feature to features that are already on your wafer. So say on your wafer you already have some features. So you have this feature and you got this feature on the other side. Okay, now you want to use a mask using this lithography process that we just talked about that you're going to put over this wafer. And you want this mask to align something exactly on top of the features that were already on your wafer. Okay? So if this was the situation that I've just drawn, this is perfect, right? So this is at the right temperature. But what happens if, say, you got a change in temperature? So you get just a 1 degree change in temperature or something like that, right? Well, this mask, maybe it expands a little bit. So that's expansion due to temperature, due to that delta temperature. Okay? And so if that mass is expanded, then what happens? So maybe you've aligned this such that these are well aligned. Okay, that aligns well. Okay, but on the other side, now that that mass is expanded, this thing is now here, and it no longer aligns with the other side of the mask. Right? So this is the problem with these masks. This is why if you have a critical alignment, you want the quartz mask. Right? Because quartz has a smaller thermal expansion coefficient than the soda lime glass mask. Okay, so the mask type is very important. Maintaining temperature around the lithography tool, very important. Right? How much does this expand? It doesn't expand much at all. Right? You can't see it expand with the naked eye, of course, right? But you're talking now about what kinds of dimensions, right? 24 nanometers? You're trying to keep them within 24 nanometers. This is going to be very difficult to do, even with 1 degree of temperature shift, even less than 1 degree of temperature shift. Okay? And so how do you solve this problem? Okay, well, it turns out the way to solve this problem is that you do not allow your mask to align this feature and that feature on 2 sides of your wafer. You never allow your mask to do that. In order to get the best resolution, you have to use what's called a stepper. So a reduction stepper, and we'll talk about that in a few minutes here. But first of all, that was the difference between these two materials, right? You like quartz. If you need very good resolution, very good alignment, you need quartz to do that. So let's talk about this process some more. So we talked about the radiation source. We talked about the mask. I guess one more thing with the mask that I'll say. The mask is kind of it is the bottleneck against what you can do and what you cannot do, even in CMOS today. Okay, so think of CMOS today. Right? How many circuits can you make in CMOS reasonably with the type of processing we're talking about now, where you get billions of transistors? Right? So the only thing that makes sense to make these days, I guess I don't want to say the only thing, but the things that make sense are high volume products. Okay, like Intel microprocessors, AMD microprocessors, cell phone chips, and that. Anything that's extremely high volume makes a lot of sense for this kind of IC processing. Okay, if it's not a high volume process, or if it's a custom type design, this starts not making too much sense. Okay, so why is that the case? That's the case because the mask here, how much does the mask cost today? Okay. Used to be that masks weren't costing that much, but I just described to you that to get this 24 nanometer, even 65 nanometer or something like that, right? It takes a lot to make that mask. Phase shifting, all sorts of things being done just to create that mask that can now get these types of feature sizes. So these mask costs are on the order of $2 million, right? And so think of that. You've paid $2 million for your masks, okay? And if you don't have a high volume application, right, that might make sense if you're going to sell 2 million parts and you want to sell them for $1 a piece. Right, it's actually more than that because you got the cost of processing on top of that, the cost of packaging, right? But if we ignore all those other costs, if your mask costs you $2 million, right, and you have 2 million parts to sell, at a minimum, you can only sell them at $1 per part. Okay? If you had 1,000 parts to sell, you're not going to sell that part. Okay? It's cheaper to make it other ways. Right? So that's the dilemma that we're faced with right now. Because our technologies have gotten so good, only high volume circuit applications make sense to use the best processing technologies that are available. And so this is part of the reason why analog designers are getting squeezed out. If you're an analog designer, don't worry, you're always going to be needed. Right? Because the world, and this is why digital is becoming so important these days. Right? Because if you think of a digital circuit, right, that's using the processes they have. And the digital circuits, right, you can you can make a mask that contains many different digital applications on it pretty easily, right? Intel CPUs are digital. And that's why people want to make more of the front ends of communication devices. Your cell phone's digital. They're all analog still right now, right? Because they sort of have to be. They've been designed. That's the best way to design them, I suppose. But digital is creeping up. As it gets faster and faster, it gets closer to the RF front end to someday where maybe the whole thing will be digital, right? And so analog designers, it's tough, right? Because you're able to design less and less these days. Right? More things are going digital. And maybe you enjoy the digital part, but the digital part, right, that almost designs itself to some extent. Right? There's less art in digital design. Digital design is more taking gates and putting them together. And a computer program can do that as well as you can to some extent. Okay, so that's sort of the problem. We still have a need for custom type circuits. So the big question is, how do we get those custom circuits that have volumes of only 100,000 or something like that? But still cannot be made using this type of technology. Okay, how do you solve that problem? That's one of the biggest dilemmas I know that the government is trying to solve right now. Because we need those custom integrated circuits, but they're starting to cost too much if we're using the latest and greatest technology. So one of the solutions to that is a lithography system that doesn't use masks. Okay, you may have heard about direct write lithography systems. E-beam systems are like this. But the problem with those is throughput is not high enough. But there are people doing research to try to create direct write lithography systems that can directly write using laser light sources or so, and many of them in parallel, your chip without the need for a mask. Okay, so you don't need to make a mask. You don't need to spend the money to do that mask. These things just write directly whatever you're trying to build. They're having problems making these things, but that could be one solution too. Allowing the ASIC designers, the analog ASIC designers back into the picture, because we need that kind of design still. We just can't do it cost effectively easily these days. Okay, so let me continue with photoresist now. And so I mentioned there's two different types of photoresist. There's a negative resist and a positive resist. And a negative resist is where the portions of the photoresist that are exposed to light, those are the portions that stay. If it didn't get exposed to light, it's gone after you do a step called development, which is really an etching step. Okay? Positive resist, exact opposite. If it's exposed to light, it goes. Everything else not exposed stays. Okay, how do these two work? They both work through photoactivation, of course. But a negative resist consists of an organic acid or some kind of resist that polymerizes when exposed to light. So you expose it to light, and what it does is it creates long linked carbon chains. Okay, and so these long linked carbon chains may look something like this. Well, I could do that in black too, right? So if you get enough spaghetti, right, that's linked together so well it's hard to pull apart, right? But once exposed to light, what this does, whoops, I got this backwards. This is negative resist. So in negative resist, you start out with just a film there, right? But once exposed to light, it converts this to long polymer chains that are sort of linked together and so very difficult to tear apart. Okay, it becomes a very strong layer, right? And that's the layer that stays once exposed to light. In a positive resist, it's the opposite thing. The photoresist starts out as this chain of polymers that's very strong. And then when it's exposed to light, it's converted to an organic acid. And since it's an acid, you just then expose it to a base. That's what developer is, like KOH, and it removes that acid. Okay? And so that's pretty much how these resists work. At least for this class, that's what I'll tell you. In 243, you'll learn something a little more detailed than that. In the end, which is better? Positive resist, a lot of people think is better. And part of that's because in a negative resist, when you have to polymerize, it's hard to do that as a step function. Right? So what you'll get is something like this, where here's where everything is strongly polymerized. Right? It's all a polymer on that side. But you still get tails that go into this. So if you were trying to create a feature like this, you would end up really creating a feature like this, which means that you're not getting as sharp a step in that photoresist as you'd like to have. Okay, positive resist doesn't have this problem, but positive resist has another problem, and that's that it doesn't stick very well to surfaces, okay, especially oxides. Okay, but you could solve that problem by putting down a primer. So hexamethyldisilazane, often called HMDS, is used before putting down positive resist. So it's a gaseous thing that you just coat the surface with. Then you put the resist on top of that, and that helps it adhere to silicon dioxide, okay, which is often the type of film that you're trying to etch. Okay, and so in the end, right, you get good adhesion. Positive resist works, so if you have a choice in which resist to use positive, because it's going to have the better resolution. And so finally, the procedure for lithography, this is just a step-by-step. This is usually what's involved with lithography. You clean the wafer. You've got to make sure it's very clean, of course, because if you have any dust particles on that wafer, that could kill a device right there. Okay, you dry the wafer, deposit this HMDS for adhesion, spin on the photoresist. Usually you have to bake the photoresist just a bit to prepare it for lithography. Then you align and expose, develop, which means put it into the base solution. And then usually what you should do is descum this. So an oxygen plasma at a very low power, 50 watts. What that does is it removes any gunk that may not have been washed away after the development. Okay, this is kind of important to do if you want very high yield in circuits and that sort. And then finally you do a post-bake, and what that does is it hardens the resist and prepares it for the etchant, because it's got to resist that etchant, so you want it as hard as possible. You don't want it too hard to the point where you can't remove it, but you want it harder than after this process here. And usually that post-bake is going to be something at a high temperature to be able to get that nice and hard. I guess exposure system optics, this is what I'll continue with in the next lecture. So we do have lecture this Thursday, just next Thursday we'll figure out what to do about that.